In this video, we are going to look at Laplace transforms. Let's start off with the definition. The Laplace transform of f of t is equal to the integral from 0 to infinity of e to the negative st times f of t dt. And we're going to use that definition to derive two formulas. The first formula we're going to derive is the Laplace transform of 1. Using the definition, that's the integral from 0 to infinity of e to the negative st times 1 dt. But that's the limit as L goes to infinity of the integral from 0 to L of e to the negative st dt. But that's equal to the limit as L goes to infinity of negative 1 over s e to the negative st evaluated from 0 to L. So I'm going to replace t with L and t with 0 and subtract the results. So it's the fundamental theorem of calculus, right? And so this is the limit as L goes to infinity of negative 1 over s e to the negative sl plus 1 over s times e to the 0. But remember, e to the 0 is 1. So this can be written as the limit as L goes to infinity of 1 over s minus 1 over s e to the sl. If s is greater than 0, this second term, when L goes to infinity, 1 over s e to the sl will go to 0. Okay? When s is 0, it doesn't make any sense because we can't have division by 0. And when s is less than 0, as L gets big, 1 over s e to the sl, that limit doesn't exist. And we want this limit to exist by design. And so we impose this restriction that s is greater than 0. And so the final limit, well, if we go back, the final limit will be 1 over s. And then from here, we're going to say the Laplace transform of 1 is equal to 1 over s. That's good. Now, if we look at number 2, the Laplace transform of e to the at, using the definition, this is the integral from 0 to infinity of e to the negative st times e to the at dt, right here. Now, just doing a little bit of algebra, I can write this as the limit as L goes to infinity of the integral from 0 to L of e to the negative of s minus a times t dt, right here. And when I do that integration, right, remember you're integrating with respect to t. And so from here, we get the limit as L goes to infinity of 1 over the opposite of s minus a times e to the negative or opposite of s minus a times t, evaluated from 0 to L. Now, applying the fundamental theorem, we get the limit as L goes to infinity of 1 over negative of s minus a e to the negative of s minus a times L plus 1 over s minus a times e to the 0. But remember, e to the 0 is 1. And so this is the limit as L goes to infinity of 1 over negative of s minus a e to the s minus a quantity times L plus 1 over s minus a. But again, we want this limit to exist. And so what I want to do is impose that restriction that s is greater than a. Because again, if s equals a, then you essentially have division by 0. If s is less than a, what ends up happening is as L goes to infinity, that first term, the limit of the first term doesn't exist. And by design, we want this limit to exist. And so when we're all said and done, we get 1 over s minus a. Okay? And so what that says is the Laplace transform of e to the at is equal to 1 over s minus a. And with those two formulas, we can derive a whole bunch of other formulas, as I will proceed to show you. Now, I want to derive something for you. Euler's formula. Euler's formula says e to the I theta is cosine of theta plus I sine of theta. Now, I claim that e to the negative I theta is equal to cosine of theta minus I sine of theta. Now, you might ask, well, why is that true? Because cosine is an even function. And so what that tells me is that cosine of negative theta is the same thing as cosine of theta. And then sine is an odd function, so sine of negative theta is the same as negative sine of theta. And then when you put all that together, you end up with e to the negative I theta is cosine of theta minus I sine of theta. Now, what I want to do is, let's do this. Let's label the first equation as equation 1 and the second equation as equation 2. So I'm going to take equation 1 and subtract equation 2. And when I do, notice how the cosines cancel out. And you end up with 2I sine of theta is equal to e to the I theta minus e to the negative I theta. And if I divide both sides by 2I, I get sine of theta is e to the I theta minus e to the negative I theta divided by 2I. And again, remember, I is equal to the square root of negative 1. It's an imaginary number. Okay. Now, let's go back. Remember that e to the I theta is cosine of theta plus I sine of theta. That's Euler. And then e to the negative I theta is cosine of theta minus I sine of theta. Now what we want to do is add them. So e to the I theta plus e to the negative I theta is 2 cosine of theta. Solving for cosine theta, I get e to the I theta plus e to the negative I theta divided by 2. Okay? Now, this is great, because from here, we're going to derive a formula for the Laplace transform of sine of kt. You do not have to do an improper integral, it turns out. Now, the Laplace transform of sine of kt is equal to the Laplace transform of e to the ikt minus e to the negative ikt divided by 2I. Now, I'm going to pull the 1 over 2I out in front of the Laplace transform. So this is 1 over 2I times the Laplace transform of e to the ikt minus e to the negative ikt. Now what we can do is split them up. And so this is 1 over 2I times the Laplace transform of e to the ikt minus the Laplace transform of e to the negative ikt. So again, it's 1 over 2I times the quantity, the Laplace transform of e to the ikt minus the Laplace transform of e to the negative ikt. But we already know the Laplace transform of e to the at. Remember, the Laplace transform of e to the at is 1 over s minus a. And notice the coefficient of t is ik. That's my a. So I get 1 over 2I times the quantity 1 over s minus ik minus 1 over s plus ik. So you can think of subtracting a negative means you add. Now I get a common denominator. So this is 1 over 2I times the quantity s plus ik minus s minus ik divided by s plus ik times s minus ik. But this is 1 over 2I times the quantity 2ik divided by s squared minus I squared k squared. But I squared is negative 1. So notice how also the 2i's cancel. It's really slick. And so this is equal to k over s squared plus k squared. and we just derived the Laplace transform of sine of kt. It's equal to k over s squared plus k squared. Right here. I'm done. Now, we could do the same thing for the cosine. The Laplace transform of cosine of kt is the Laplace transform of e to the ikt plus e to the negative ikt divided by 2. Now, if you don't mind, I'm going to pull the 1/2 out in front and pull apart those Laplace transforms. So what I'm saying is I get 1/2 times the quantity, the Laplace transform of e to the ikt, plus the Laplace transform of e to the negative ikt. So this is 1/2 times the quantity, 1 over s minus ik plus 1 over s plus ik. So I'm just relying on this formula, this one, right? The Laplace transform of e to the at is 1 over s minus a. I'm relying on that the whole time so far. So this is 1/2 the quantity, s plus ik plus s minus ik divided by s plus ik times s minus ik. So notice how the ik's cancel out, and I get 1/2 of 2s divided by s squared plus k squared. The 2's cancel, and the Laplace transform of cosine of kt is s over s squared plus k squared. So we derived now 2 formulas relying on our knowledge of 2 other formulas. Now it gets better. Suppose I want the Laplace transform of cosine squared of kt. Well, that's the Laplace transform of 1 plus cosine of 2kt divided by 2. Pull the 1/2 out in front, and I'm going to take 1/2 times the quantity, the Laplace transform of 1, plus the Laplace transform of cosine of 2kt. Now, this is 1/2 the quantity, 1 over s plus s over s squared plus, now we have to be careful here because when it was cosine of kt, it was s over s squared plus k squared, but it's 2kt, so it's going to be s over s squared plus 2k quantity squared. Okay. Now, we just get to do a little algebra, getting a common denominator, right? And also remembering 2k raised to the second is just 4k squared, right? 2 times 2 is 4, k times k is k squared. So this is 1/2 the quantity, 1 over s plus s over s squared plus 4k squared. And then we get 1/2 the quantity of s squared plus 4k squared divided by s times s squared plus 4k squared plus s squared over s times s squared plus 4k squared. Just common denominator stuff. Coming over here, and we just get to do some algebra. This is 1/2 the quantity, 2s squared plus 4k squared divided by s times s squared plus 4k squared. Factor out a 2 in the numerator, and you notice I get 1/2 the quantity, 2 times s squared plus 2k squared divided by s times s squared plus 4k squared. The 2's cancel, and I got another formula. The Laplace transform of cosine squared of kt is s squared plus 2k squared divided by s times the quantity, s squared plus 4k squared. It's really, really slick, right? That's our third formula that we derived just knowing 2 other formulas, you know. So, and in fact, we can derive a 4th formula. So if you notice, the Laplace transform of sine squared of kt is equal to the Laplace transform of 1 minus cosine of 2kt divided by 2. So this is 1/2 the quantity, and in that quantity, we're taking the Laplace transform of 1 and subtracting the Laplace transform of cosine of 2kt. So this is 1/2 the quantity of 1 over s minus s over s squared plus 4k squared, right here. And then getting a common denominator, we're going to write the following. This is 1/2 the quantity s squared plus 4k squared minus s squared divided by s times s squared plus 4k squared. So notice how the s squareds cancel, right? And then we get 1/2 of 4k squared divided by s times s squared plus 4k squared. And then 2 goes into 4 2 times. And so I'm done. The Laplace transform of sine squared of kt is equal to 2k squared divided by s times the quantity s squared plus 4k squared. And what I want to do is I want to show you 2 more with the time we have. If I look at cosh of kt, hyperbolic cosine, this is e to the kt plus e to the negative kt, all divided by 2. So we're essentially going to do the same thing. I'm going to take the Laplace transform of both sides. So the Laplace transform of cosh of kt is the Laplace transform of e to the kt plus e to the negative kt divided by 2. Okay? Now, pull the 1/2 out in front. And then this is equal to the inside, right? Let me say it this way. Pull the 1/2 in front, and inside the brackets, we're going to put the Laplace transform of e to the kt plus the Laplace transform of e to the negative kt, like so. So this is 1/2 of 1 over s minus k plus 1 over s plus k. So you might notice I'm applying those first 2 formulas that we derived over and over and over and over again. And then this is 1/2 of s plus k plus s minus k divided by s squared minus k squared. So far. And this is 1/2 of, and then s plus s is 2s, so I get 2s over s squared minus k squared. The 2's cancel, and I'm finished. So the Laplace transform of cosh of kt, this is, notice how 2's go away, and I get s over s squared minus k squared. So everything can be derived, or I shouldn't say everything, but quite a number of formulas can be derived just knowing those 2 fundamental formulas. And that's the Laplace transform of 1 and the Laplace transform of e to the at. Okay? And then just this last one, if we look at sinh of kt, this is e to the kt minus e to the negative kt divided by 2. And then I get the Laplace transform of sinh of kt. Okay? So if you don't mind, I'm going to pull the 1/2 out in front, and then I'm going to multiply by the Laplace transform of e to the kt minus the Laplace transform of e to the negative kt. It's going to follow a similar pattern to cosh in terms of derivation. Okay? So from here, we get 1/2 the quantity, and then we get 1 over s minus k minus 1 over s plus k. Now, if I get a little common denominator here, the common denominator will be the product of those denominators. So, in other words, it's s squared minus k squared. In the numerator, I get s plus k, right? Minus s minus k. But the s's are going to go away. And we get 1/2 of. So when the s's go away, we're just left with k minus a negative k, which is 2k, over s squared minus k squared. Okay? And the 2's cancel, and I'm finished. The Laplace transform of the hyperbolic cosine or cosh of kt is k divided by s squared minus k squared. And that'll do it for this video. This is a video on Laplace transforms, and this would be found in a differential equations class. So, okay, thank you.